All right, let's dive in. The first thing we're going to talk about, and we alluded to this a little bit earlier, is the idea of equivalent fractions, two fractions that are equivalent. If they're equivalent, what that means is that they have the same value. And one of the things we're going to work on is creating equivalent fractions. Before we start doing that, before we start going down the road of creating equivalent fractions, I just sort of want to give some examples of equivalent fractions. For example, if we have the fraction 1/2, well, a fraction that would be equivalent to that would be 2/4. They have the exact same value. It's just written with different numerator and different denominator. And as you look at this, you can kind of see that if you wanted to write 1/2 as 2/4, you're multiplying the denominator by 2, multiplying the numerator by 2, and that's how you arrive at an equivalent fraction. It doesn't necessarily have to be 2. 1/2 would be the same thing as 3/6. Same value. Those are equivalent fractions. And essentially what's happened here is going from 1/2 to 3/6, we've multiplied the denominator by 3. So to keep the value the same, we also have to multiply the numerator by 3. And that's how we're going to work to create equivalent fractions. And honestly, going the other direction, if we wanted to reduce a fraction like 3/6 to lowest terms, what we'd be looking at is can we divide the numerator and denominator by? If we can divide the numerator and denominator by the same number, then we can reduce that fraction. And you could divide by 3, and you could reduce 3/6 down to 1/2. So this going back and forth between equivalent fractions is something we want to make sure we're comfortable with. Let's take a look at one. Create a fraction that is equivalent to 3/8 that has a denominator of 72. I'm actually going to set up a poll for this one. I want you to create a fraction that is equivalent to 3/8, but your new fraction has a denominator of 72. So to make sure your new fraction has a denominator of 72, but make sure it is equivalent to 3/8, meaning it has the same value as 3/8. I'll give you a little more time on this one, but really don't overthink it. We're just creating a fraction that is equivalent to 3/8, but our new one has a denominator of 72. So we know we're going to have 72 on the bottom of the fraction that we're going to create. So really what we're trying to figure out is, what does the numerator have to be in this new fraction that we're creating? This is a technique that we're going to use for several different types of questions. So I want to make sure we're comfortable with it. We'll go another 30 seconds on this and then we'll talk through it. You may see a question just like this one in the homework or on a quiz or an exam that just says, create a fraction equivalent to the given fraction that has this new denominator. All right, let's see how we're doing. Strong agreement, not unanimous, and we've got answers spread all the way through those. All right, let's take our time as we go through this, and we may look at one more example afterwards. So the idea here is we're trying to create a new fraction that is equivalent to 3/8 that has a denominator of 72. Well, we have to think, what is it I have to do to this 8 to turn it into 72? We have to multiply by 9. And so if we multiply the denominator by 9, we also have to multiply the numerator by 9, and 3 times 9 will give us 27. So a fraction that's equivalent to 3/8 that has a denominator of 72 would be 27 72nds. Just to revisit this a little bit, if we had the fraction 2/7 and we wanted to rewrite it with a denominator of 35, take a minute. Don't type it in right away, even if you do see it right away, but take a minute and decide what number would need to go here in that numerator to make this fraction equivalent to 2/7 but have a denominator of 35. Take a minute, don't type it in yet, and think about what number would have to go there in order for that to be a true statement. I'll tell you when you have a green light to type it in. I just want to make sure that anybody who had a little bit of trouble with this one gets another chance to do another one of these. And so essentially what we're doing here is create a fraction equivalent to 2/7 with a denominator of 35, and it's what would have to go in this numerator is what we're trying to find out. Okay, what would need to be in that numerator there? What number would be in the numerator? All right, we've got several 10s over there. I hope everybody is on board with that 10. Perfect, very good. Thank you, everybody, for typing those in. Essentially, what has to happen to 7 to turn it into 35? Well, we multiply by 5. So what has to happen up here? We have to multiply by 5, and 2 times 10 would be, or 2 times 5 would be 10, and we end up with 10/35 would be a fraction that's equivalent to 2/7 that has a denominator of 35. Let me know if you have any questions about creating equivalent fractions. Reducing fractions. And I touched on this just a little bit when we looked at how to create an equivalent fraction. Now we're going to go the other direction. And what we're going to do is we're going to divide the numerator and the denominator by the same thing. An example of that would be if we started out with the fraction, maybe not that, maybe 30 over 42. So 30 42nds. We have that fraction, and we're supposed to reduce this as much as possible. There's a couple of different ways that you can go. One way that I tend to like very much is if I look and I see that they're both even numbers, then I know they're both divisible by 2. Now, it's possible that there's a bigger number that I could divide into these, and that would get me to my reduced fraction faster, but those are both even numbers, so I can divide the top by 2 and have 15. I can divide the bottom by 2 and get 21. All right, that's reduced from the original, but it's not reduced as much as possible. Now I don't have even numbers, so I have to think a little bit like, what is it that could go into 15 that could also go into 21? What could I divide both of those numbers by? Excellent, Dulcie, Moyle, perfect. And there's a little bit of trial and error involved in this. Well, two won't go in, but how about three? Yeah, three would. That's great. And if three wouldn't, then you could try five. And if five wouldn't, you could try seven, and so on and so on. If they're both even numbers, dividing by two is an awesome way to go. You don't have to, though. We'll look at that in just a minute. But then here I could also say, okay, well, I could divide that 15 by 3 and get 5 on the top. I could divide the 21 by 3 and get 7 on the bottom. And so what we've done here is we've reduced 30, 40 seconds down to 5/7, and those can't reduce anymore. Those are both prime numbers. Nothing else will go into them but 1 in themselves. So 5/7 is this has been reduced as much as possible. It's certainly possible for numbers like 30 and 42 that some of you might have seen this at the beginning instead of said, yeah, I get your even number thing, but right away I can see that I could divide each of those by 6. I could take this 30 over 42 and I could divide the numerator by 6 and I could divide the denominator by 6. And when I do that, 30 divided by 6 is 5, 42 divided by 6 is 7, and sure enough, that gets you to the same place. I did the 2 just because if they're both even numbers, that feels comfortable. But if you happen to see right away, hey, 6 will go into both of those, then that's great. You can go ahead and just divide by 6 right out of the gate and reduce that fraction. I do want to point out that dividing by 2 and then dividing by 3 is the same thing as dividing by 6. Not exactly a division property that we're going to talk about. We could talk about this as a multiplication property a little bit, that if we multiply by a half and then multiply by a third, that's the same as multiplying by a sixth. We could say that. We won't talk about this with division, but the reality is if we divide by 2 and then after that we divide by 3, the net result is the same as dividing by 6. Okay. Are there any questions about reducing fractions? All right, so we've created equivalent fractions, we've reduced fractions. The next thing I want to take a look at with you is ordering fractions. If we wanted to order these fractions from least to greatest, 3/4, 2/5, and 5/6. Now, off the top of my head, I'm not really sure. 3/4, 2/5, 5/6. I'm not sure which is going to be the biggest and which is going to be the smallest. If we want to organize those from least to greatest, one of the ways that we can do this is we're going to rewrite these so that they all have the same denominator. We are going to create equivalent fractions and we're going to create those in such a way that they all have the same denominator. There's a little bit of effort that goes into this. We have to think, what can I write as my new denominator? And I need something that 4, 5, and 6 will all go into evenly. Something that 4, 5, and 6 will all go into evenly. Anybody have something that comes to mind that 4 and 5 and 6 will all go into? And there's more than one right answer here. So it's okay if we all don't have the same thing. Okay, 60 maybe, 20 maybe. Anything else anybody wants to throw out there? Oh, all right, Courtney. Gotcha. I was going to say, if we do 20 divided by 6, I'm not sure that one's going to play out so great. So good. I'm glad you caught it. That's awesome. Now, you're not wrong, though. The 4 and the 5 will go into 20. It's just that the 6 wrecks it. So that's no good. But if we want to find something these will go into, Moyle in 60 is excellent. But one strategy you have here, and it won't necessarily give you the smallest number that they'll all go into, but if you do 4 times 5 times 6, that will absolutely give you something that all three of them will go into. And that would be 4 times 5 is 20 times 6 is 120. So we could absolutely use 120 as our denominator for our equivalent fractions. That's great. If you happen to see it right away that, well, you know what? 4 will go into 60, and 5 will go into 60, and 6 will go into 60. Or maybe what Moylan did there, I'm not exactly sure, is took the two biggest ones and said, well, 5 times 6 is 30, but 4 won't go in. But if I double that and then it's 60, now 4 will go in, and so I can use 60. Maybe that's the strategy. For some of you, that might be like, what the heck? Why would you go through all that trouble? If I could just multiply 4 times 5 times 6, I'm going to do that. Great, no problem there. It is true, though, all three of those numbers will go into 60. So we're going to look at this both ways. If we use that 60, what we're going to do then is we're going to say, okay, I need to write 3/4 with a denominator of 60. And so the first thing I have to do here is think, what do I have to multiply 4 by to get 60? Well, off the top of my head, I don't know. But what I can just do is I can do 60 divided by 4, and I'll find that out. And let's see, 60 divided by 4 is 15. So sure enough, if we multiply the denominator by 15, we can multiply the numerator by 15. And I don't know what 3 times 15 is, but I don't need to. That's 45. So 3/4 becomes 45 over 60. All right, now I'm going to do the same thing with 2/5. 2/5 has to become something over 60. Well, what do we multiply 5 by to get 60? I don't know, but 60 divided by 12 will tell, or excuse me, 60 divided by 5 will tell me that that's going to be 12. And so we'll multiply the numerator by 12 also. And 2 times 12 is 24 over 60. So what we found out so far is that 3/4 is equivalent to 45 over 60. 2/5 is equivalent to 24 over 60. And we have one more to do, and that's 5/6. And that's going to be something over 60. This one I can actually do in my head. That's times 10. And so that'll be 50 over 60. This problem started out with us trying to compare 3/4, 2/5, and 5/6 to see which one is the biggest. I have no idea. Now it's become a much different question. Now 45/60, 24/60, and 50/60. Because they all have the same denominator, I can see that this is the smallest, this is the middle one, and this is the biggest. And so if I want to write these from least to greatest, I'm going to say, well, 2/5 is the smallest, and then 3/4 is the next, and then 5/6 is the biggest. And we've written those from least to greatest. And the way we did it was by creating equivalent fractions, because those we were able to compare. I promised I'd do this with the 120, so I'll do that here in just a second. But first, are there any questions about what we did there? All right, just to show it with the 120, if you don't really want to think about what am I going to use for my new denominator, you have the ability to just say, I'm going to go 4 times 5 times 6, and whatever that is, that's going to be my new denominator that I'm going to use for all three fractions. So if we do that, let's see, then we'll have, okay, I need to rewrite 3/4 as something over 120. And again, I don't know what multiply 4 by something to get 120, but I can just do 120 divided by 4, and I can see that's times 30. So I'll multiply the numerator by 30. Then I'll do the same thing with 2/5. I need to rewrite that with a denominator of 120. I don't know what 5 multiplies by to get 120, but I can divide it and see that that's 24. And then 24 times 2 gives me 48. And we're saying that 2/5 is equivalent to 48 over 120. If you see any numbers that you're not sure where they came from, just let me know. And then finally, we have to do the same thing with 5/6. 6 times something is 120. divide it, that's 20. So 20 times 5 is 100. And now what I can do is I can look at those three numbers and I can say, well, I have 90 over 120, 48 over 120, and 100 over 120. That's the smallest, that's in the middle, and that's the biggest. And it's the same result we got the other way. 2/5 is the smallest, 3/4 is in the middle, and 5/6 is the biggest. So if you happen to notice that a number like 60 works, and that's your, that's going to be your new denominator, that's great. If not, you can always multiply them together and you'll wind up in the same place. Let's try one. Order those fractions from least to greatest. 5/8, 2/3, 7/12. I'll set up a poll for this, and then you can let me know what you think. So we're creating equivalent fractions, and then we're looking to see which one's the smallest, which one's in the middle, which one's the biggest. And you can see how equivalent fractions plays a huge role in what we're doing today. It's actually the bulk of it. How about we go another 20 seconds and then talk through this one? If you need more time, just let me know. All right, see where we are? Almost unanimous, definitely strong agreement there. That's excellent. Okay, so there's a couple of ways you could go here. Obviously, one way when you think, I'm going to rewrite these as equivalent fractions, I need to find a denominator. One way is to go, well, what's 8 times 3 times 12? And that is perfectly fine. There is nothing wrong with that. I will say using a denominator of 288 will make the numbers a lot larger. And sometimes if you go that way and make the numbers a lot larger, it's possible to make a mistake in there somewhere. As you look at this, well, 8 times 3 would be 24, and 12 will go into 24. So really, while there is nothing wrong with using 288, we can get away with using 24 here. And so if I say 5/8 with a new denominator of 24, multiply by 3 on the bottom, So multiply by 3 on top, and that's 15/24. Again, please let me know if you see something that you're not sure where it came from or isn't making sense. We'll do it with the next one, 2/3. And we're going to rewrite that with our denominator of 24. That's multiply by 8. And 2 times 8 would be 16/24. Well, those two are awfully close together, but 2/3 is a little bigger. And then finally 7/12 with something over 24. That's times 2. So we'll multiply the top by 2 and have 14/24. Boy, these are all really close to each other. But as it turns out, 7/12 is the smallest, 5/8 is next, and 2/3 is the biggest, because 14/24, then 15/24, and then 16/24. So writing these from least to greatest, we'd have 7/12, and then 5/8, and then 2/3. And you could absolutely do it with the denominator of 288. If anybody wants to see it done that way, you can let me know. The process is going to be the same. It's just instead of 24 as our denominator, we'll have 288. You bet, Stephanie. Sure thing. I'm going to go ahead and erase this. And we'll do it with 288. Okay. So the first thing I need to do is rewrite 5/8 with 288 as the denominator. Now, the last time I was able to do this in my head, but 8 times what is 288? I have no idea. So the way that I'm going to figure that out is I'm going to do 288 divided by 8, and that's 36. So we had to multiply by 36 on the bottom. So we're going to multiply by 36 on the top also. And so we'll have 5 times 36 is 180. So what we're seeing there is that 5/8 is the same as 180 over 288. Then we'll do this with 2/3. 2/3 is going to be something over 288. And here again, I don't know what multiply 3 by something to get 288. I don't know what that is, but I can divide 288 divided by 3. And I'm going to have to multiply by 96. And if we multiply by 96 on the bottom, we'll have to multiply by 96 on the top. 96 times 2 will be 192. And so 2/3 is the same as 192 over 88. And then finally, we'll do this again with 7/12 is going to be something over 288. Here again, I don't know what 12 times something is 288, so we can just divide that. And that's 24. If I multiply the bottom by 24, I have to multiply the top by 24. And when I do that, we get 168. And now what I end up with is, let's see, I wanted to write these least to greatest. So 180 over 288, 192 over 288, and 168 over 288. Well, 168 is the smallest, so that's going to go first. 180 is the second smallest, so that's in the middle. And 192 is the biggest, so that's going to be last. And so again, we end up with 7/12, 5/8, and 2/3. No problem. No problem at all. Here's another type of problem. It's kind of like ordering fractions, but not exactly. Which of these fractions is closest to 1/4, 3/8, or 2/5? I'm going to set up a poll for this one. There's only 2 choices, but which one is closest to 1/4, 3/8, or 2/5? So, which one's closer to 1/4? 3/8, 2/5. They're the same distance from 1/4. Or you can't tell. I don't know. Not enough information. Let's go another 15 seconds and then talk about it. Let me know if you need more time. We're not in a hurry. We've got plenty of time today. Okay, not unanimous, but pretty close. That's good. If anybody has questions when we talk through this, please don't hesitate to ask them. All right, let's see what we've got here. So, which is closest to 1/4? The idea here is going to be very similar to what we did with putting them from least to greatest, in that what we want to do is we want to write these with the same denominator. And honestly, because we're trying to compare those to 1/4, what we want to do is we want to write all three of these fractions with the same denominator, and then we want to figure out which one's closest to 1/4. So we need a denominator that works for 4, 8, and 5. Here again, if you want to, you can absolutely do 4 times 8 times 5 and have whatever that is. 4 times 8 times 5 is 160 as your denominator. And we'll do it both ways. So you could use 160 as your denominator. Some of you might look at this and say, well, 8 times 5 is 40, and 4 will go into 40. So I'm just going to use 40. So we're going to do this both ways. We'll do it with a denominator of 40. We'll also do it with a denominator of 160. First, the number that we're concerned with, the 1/4, if we want to write that with a denominator of 40, then let's see, we've got to multiply by 10 on the bottom, 10 on the top. So we want to know which of these is closest to 10/40ths. All right, so let's see. I want to write 3/8 with the denominator of 40. Multiply by 5 on the bottom, multiply by 5 on the top. That'll be 15/40ths. So what we're saying, never forget the big picture here. We're saying 15/40ths is equivalent to 3/8. But for this particular problem, it's more convenient for me to look at it as 15/40ths because I want to know how close it is to 10/40ths. Then finally, we have 2/5 that we need to rewrite with a denominator of 40. We're multiplying the bottom by 8. So we'll multiply the numerator by 8. 2 times 8 will be 16. And so what I'm saying here then, at the heart of this question is 15/40ths or 16/40ths closest to 10/40ths? And since this is 5/40ths away, this is 6/40ths away, so this would be the one that's closer, which means 3/8 is the fraction that's closer to 1/4. We'll look at the exact same thing with 160 as our denominator. if we have 1/4 and we want to rewrite that with 160 as our denominator, I'm not positive. How about I do 160 divided by 4? So we're multiplying by 40. So we'll multiply the numerator by 40. That'll be 40 over 160. That's our target. That's our goal. That's what we're trying to get closest to. And I'm going to rewrite 3/8 with 160 as the denominator. It's probably 20. I'm just going to make sure. 160 divided by 8. Okay, yeah. So we're going to multiply by 20. And 3 times 20 in the numerator will be 60. And then we also have to do 2/5 with 160 as a denominator. I don't know what that is. So 160 divided by 5 is 32. So we have to multiply by 32. And 2 times 32 would be 64. Again, we're saying 2/5 and 64 1/60ths are equivalent. They have the same value. Now it's a question of which of those two fractions I just worked on is closest to 40 over 160. Well, 60 over 160, 64 over 160. This one is too big. This one is the one that's closer to 40 over 160. So again, and we better get the same answer. 3/8 is closer to 1/4 than 2/5 is. So we talked about equivalent fractions. We talked a little bit about reducing fractions. And then we've sort of ordered fractions in terms of least to greatest and which one's closest to a certain position. Is there any questions about any of that before we move on and start talking about what's going to lead us to greatest common factor? All right, terrific. Prime factorization. You may recognize this when we start doing it. What we're going to do is we are going to take a number and break it down into a product of prime numbers. Just as a reminder, prime numbers are only divisible by 1 and the number itself. So, and you don't have to memorize these or anything like that, but 1 is a prime, 2 is a prime, because the only thing that will go into 2 is 1 and 2. 3 is a prime, because the only thing that will go into 3 is 1 and 3. 4 is not a prime, because it's divisible by 2. 2 will go into it, so it's not a prime. And in fact, no even numbers bigger than 2 are prime numbers, because 2 will go into all those. But 5 is a prime, because the only thing that will go into it is 1 and 5. 6, not a prime, because 2 will go in. 7's a prime. The only thing that will go into 7 is 1 and 7. 8, not a prime, because 2 will go in. 4 will go in also, but that's not important. If there's anything but 1 and the number, it's not prime. 9. Well, 3 would go into 9, so it's not prime. 10, that's not prime because it's even. 11 is prime. And so what we're going to do is we're going to take every number and break it down to a product of primes. That is, what prime numbers can we multiply together to get a specific number? Here's an example. We're going to look at the number 84. And we're going to find the prime factorization of 84 by breaking it down. And like I said, you may have called this factor trees somewhere along the line because that's how it works. Now, there's a lot of different ways to write 84. And actually, I'm going to do this 2 different ways. I'm going to do it over here, and I'll do it again with a different approach. But I'm going to start. The first thing I think of is, hey, that's an even number, so I can divide it by 2. And so what we're going to write is that 84 is 2 times 42. And then I go, well, heck, 42 is an even number. So I could rewrite that as 2 times 21. And once I get a prime number at the end of one of these paths, then I stop breaking it down. I can't break down 2 any further. So I know I'm at the end of that line. That 21, though, I could break that apart into primes. How could I write that 21? What could I write with the 21? What 2 factors? Perfect, Courtney. 7 and 3. you'll indulge me, I'm going to write it as 3 times 7, but it means the exact same thing. And so now we've broken this down into prime numbers. You look at the end of each of these rows, and what you see is we have a 2, 2, 3, and 7. Those are all prime numbers because I can't break them down any further. And what we're going to say is that the prime factorization of 84 then is 2 times 2 times 3 times 7. We've rewritten the number 84 as a product multiplication of prime numbers. In fact, we're going to go a little bit further than that, and we're going to say these two together here. We're going to use an exponent for those. 2 times 2, that's just 2 squared times 3 times 7. So our prime factorization of 84 is 2 squared times 3 times 7. And you don't have to, but it's sort of customary to write these down from least to greatest, the 2, then the 3, then the 7. So we write them from least to greatest, but that's fine in the prime factorization. Now, I mentioned I was going to do this a different way, and that's what's coming next. So if I've got this 84 here, and you're thinking, well, I don't know, since that's got a 4 in it, the first thing I saw was I could divide it by 4. 84 divided by 4 is 21. So what happens if instead of 2 times 42, what if I do 4 times 21? That's a great question. Right away, I saw 4 would go into this. So I want to do that. Okay, good. That 4 we can break down into 2 times 2. And then those are at the end of their run. The 21 we could break down into 3 times 7. And sure enough, we end up in the exact same place. 2 times 2 times 3 times 7. So there's not a right way or a wrong way to start breaking down the number. You just keep breaking it down until you can't break it down anymore, and you are going to land on one unique prime factorization for any number that you start with. I didn't specifically put in a prime factorization practice, but we can certainly do one like that if you want. But we are going to use this in greatest common factor problems, so you're going to see a bunch more of them. Let's do another one. Greatest common factor. The greatest common factor is the biggest number that will go into two numbers. That's a little clumsy, isn't it? Okay. If we want to find the greatest common factor of 45 and 60, what we're looking for is what is the biggest number that will go into 45 evenly that will also go into 60 evenly with no remainder. So if we divide by this number, it'll go into 45 evenly. It'll also go into 60 evenly with no remainder. The way that we find the greatest common factor is by finding the prime factorization of each number. First, we find the prime factorization of each number. So we're going to find the prime factorization of 45, and we're going to find the prime factorization of 60. As we do that, let's see. You might do these different, but hopefully you'll end up in the same place. I'm going to try to go unorthodox here. So 45, I'm going to say that that's 3 times 15. I would expect almost everybody to say 9 times 5, which is why I'm doing it this way, is to show you that no matter which road you take, you'll end up in the same place. And that 15 would be 3 times 5. And so I end up with a prime factorization of 45 as, let's see, that's 3 times 5, which when I rewrite that with exponents, that's going to be 3 squared times 5. So that's my prime factorization of 45. Let me know if you have any questions about that at all. Now we're going to do prime factorization of 60. Well, let's see. Again, I'm going to go unorthodox here. I'm going to do 3 times 20. Most of you probably did 2 times 30. That's okay. We're going to take different roads to get to the same place. And that 20, well, that's 4 times 5. And then that 4 is 2 times 2. Now I'm at the end of all my roads. And so what I've got over here is And you kind of have to look for them sometimes. It's 3 times 2 times 2 times 5. So my prime factorization of 60 then, I'm going to rewrite it with exponents, is going to be 2 squared times 3 times 5. One thing you can do if you're not sure if you have the right prime factorization is you can go ahead and do the multiplication in C. Over here on the left for the number 45. 3 squared times 5. Well, that would be 9 times 5. Okay, that works. That's 45. And over here on this one, a little bit more involved, but we could do it. 2 squared would be 4 times 3 would be 12 times 5. Sure enough, that's 60. So you can check your prime factorization really easily by multiplying and see if it gives you the number that's supposed to. Okay, great. We did the prime factorization part. I still don't have the greatest common factor. Where's that coming from? Here's where that comes from. We keep whatever they have in common. We're looking for the greatest common factor. What will go into each number evenly with no remainder? And so what we do is we use the prime factorization and then we keep whatever those prime factorizations have in common. Whatever's in this prime factorization and in this prime factorization. It's intersection back from our set theory stuff. It's always nice when stuff comes back around. We're looking for what the overlap is. What do they have in common? And as I look over here, I see a couple of 3s. Over here only has 1 3. So what they have in common then is just one single individual 3. That's it. We can't keep both of these 3s because this number only has 1 3. So we just keep 1 3. All right, what else do they have in common? Well, this has a 5 in it. This has a 5 in it. So we'll keep that 5. If you're thinking, well, what about these 2s over here? We got to do anything with those? No, we're not. And the reason we're not going to do anything with those 2s is because there's no 2s over here. So we're not going to keep those. We only keep the things that are in both sets, the thing they have in common. We end up with 3 times 5. And our greatest common factor then is 15. The biggest number that will go into 45, that will also go into 60, is 15. You might have thought, well, heck, I could have told you that right away. 15 times 3 and 15 times 4. This is the easy one. You're right. It's not a hard one. But I promise I'll give you a chance to practice something that might not be so obvious right out of the gate. I think it's good if it's obvious right out of the gate because you believe that 15 really is the answer. Any questions about what we did there before I have you practice one where you find the greatest common factor? Awesome. Thanks, Nicole. That's good. That helps me move along. All right. So what I want you to do is find the greatest common factor of 36 and 90. So find the greatest common factor of 36 and 90. I'm going to set up a poll for this. What's the biggest number that will go into 36 with no remainder that will also go into 90 with no remainder? And to keep this from being purely multiple choice, I'm going to wait just a minute or two before I post that poll. I want you to have a chance to work through this. Find the greatest common factor of 36. Find the greatest common factor of 90. Keep what they have in common and multiply those things together. I don't know if I said that last time. Whatever they have in common, we multiply those terms together to end up at our greatest common factor. Okay, I'll go ahead and throw the poll up so that you can respond to it. All right, we'll go another, let's say 40 seconds on this and then talk about it. It can take a little while to come up with the greatest common factor for each, and then deciding what do they have in common, and then multiplying those together. Okay, let's see what we've got for this one. Okay, so we have a answer that's more common than the others, but we are spread around a little bit. So let's be careful when we talk through this one. Please let me know if you have any questions or you see anything that you're not sure where it came from. So the first thing we're going to do is find the prime factorization of each of those numbers. So the prime factorization of 36. Remember, you could take a different road to get here. I'm going to do 6 times 6. And then that one is 2 times 3. And this one's also 2 times 3. So what I wind up with here is 2 times 2 times 3 times 3. And so when we write that prime factorization, it'll be 2 squared times 3 squared. That's my prime factorization of 36. If you don't see it, or if it doesn't make sense where it came from, please just ask. And then 90. There's a couple different ways you could go here. My instinct with an even number is to go 2 times 45. And then, okay, 45, well, 5 will go into that. 5 times 9. And then this one is 3 times 3. And so what I've got at the very end here is 2 times 3 times 3 times 5. So if we write the prime factorization of 90, that's going to be, let's see, where do I want to put that? How about over here? 2 times 3 squared times 5. So there's my prime factorization of each. Now, in order to find the greatest common factor, what I want to do is I want to see what do they have in common and then multiply those together. So I'm going to keep whatever they have in common. So as I look over here on the left, this has 2 2's. It has 2 squared, so it has 2 twice. This one only has 2 once. So what they have in common, where they overlap, is just a single individual 2. That's it. Then this one has 3 squared. This one also has 3 squared. So I can keep 3 squared. I can keep both of those 3's. I can keep 3 squared. Since this one has 2 3's in it and this one has 2 3's in it, I can keep them both. And so I wind up with 2 times 3 squared as everything that they have in common. What about this 5 over here? Well, that 5 is wonderful, but there's no 5 over here, so we're not going to use that 5 when we go look for the greatest common factor. So now what I end up with is, let's see, 2 times 3 squared, or 2 times 9, or 18, as the greatest common factor of 36 and 90. 18 is the largest number that will go into 36 that will also go into 90. Are there any questions about that before we do a little bit of problem solving? Did you wind up with 18? I don't remember. Oh. So I'm not sure what you did, Leslie. We could definitely talk through it and see what it is, because if we want to clear up your mistake and misunderstanding, that would be worth our time, I think. Okay, so let's do that. So if you break 90 apart as 9 and 10, and then this 9 will go 3 and 3, and the 10 will go 2 and 5. And so then we wind up with 2 times 3 squared times 5, which is the same thing we ended up with. Ah, there it is. Okay, very good. When we can find our mistakes, that's awesome. That's great. Okay, so this 10 became 5 and 5 for you because of addition rather than multiplication. Yep. All right. Very good. Perfect. We found a mistake in there. That's excellent. Very good. Outstanding. So yeah, be a little bit careful with these. It's really easy to do something like that and go 10 is 5 times 5, and then the whole thing goes south. Outstanding. Very good. I'm really glad we talked through it together. I'm glad we looked at it. That's terrific. Okay. Any other questions about greatest common factor before we do a little bit of problem solving? Okay. You started cooking a meal at 5 p.m. and it will be done at 7:30 p.m. When at 6 p.m., what fraction of the cooking time remains? So there's a couple ways to look at this problem. And first, we want to digest it a little bit. And I don't know, in some ways, you could sort of think, hey, this kind of feels like a length model question. I started at 5, it'll be done at 7:30, and right now it's 6 o'clock. What fraction of the cooking time remains? That's just sort of a way to visualize what it is that's going on here. I don't think we're really going to use the length model to solve this, but it gives us a visual, which could be really helpful. So what fraction of the cooking time remains? There's a way you could do this that works and it's fine, but I wouldn't do it this way. You could say, well, let's see, don't write this down. That'd be my advice. The entire cooking time is 2.5 hours, and the fraction that remains is 1.5 hours. And so really what this question is what fraction of 2.5 is 1.5? Yeah, that's nice, but boy, is it kind of clumsy. And honestly, as I look at my length model there, I probably need to put that 6 in a little more accurate spot. How about we put the 6 over here? And I want to know what fraction of the cooking time remains. All right. I said I wouldn't do it the way I was just talking about it. It's because those fractions are a little bit hard to manage and unwieldy. But that is the way we want to do this. The entire cooking time that is available there, yeah, it's 2.5 hours. But instead of hours, I don't want to introduce fractions into this problem if I don't have to. At least not now. 2.5 hours would be how many minutes? Let's see, 2.5 hours would be how many minutes? You'll see why that we're going to convert this to minutes when we work on it, I promise. 2.5 hours would be how many minutes? Kind of a base 60 question, which is always kind of cool. 150, that's right. We're just multiplying by 60. 2.5 hours, if we multiply the 2.5 by 60, we get 150 minutes. So the entire cooking time is 150 minutes. And then the amount of time we have left from here to here. How many minutes is that? From 6 to 7:30. Way easier in our head to do that one. From 6 to 7:30 is 90 minutes. So when I go back and I look at this question and it says, what fraction of the cooking time remains? Well, 90 of the 150 minutes is what remains. So essentially what we've got here is we're going to create a fraction that is 90 over 150. This is the fraction of the cooking time that remains. There's 90 minutes left. That's the fraction of the entire cooking time. That's 150. So 90 of the 150 minutes remains, and all we need to do is reduce that fraction. That's it. So you read this question and it feels kind of strange, and I'm not really sure I really understand what's happening here. And what we want to do is we want to come up with a fraction that says how much cooking time is left. And there's 150 minutes total. There's 90 minutes that remain. So we just need to reduce that fraction. There's a lot of ways you could go here. It looks to me like they're both even numbers. So you could divide by 10 right out of the gate, or excuse me, by 2 right out of the gate. But because of these zeros here, I'm going to go ahead and divide by 10 right out of the gate and see that that's 9/15 of the cooking time remains. 3 will go into both of those. 9 divided by 3 is 3. 15 divided by 3 would be 5. And so, as strange as it is, 3/5 of the cooking time remains. I hope that feels better now that we've done it than it might have at the beginning. I do want to point out that the reason I wouldn't do it this way, the 1.5 hours remains over 2.5 hours total, is that this is going to be really clumsy to work with and try to reduce. But if we work it in terms of minutes, then all we need to do is reduce that 90 over 150. It would absolutely work if you did an hour and a half over 2.5. You could absolutely get to the same result. I just think it's clumsier. And I think a question like this is easier to work with when we have a whole number on top and a whole number on the bottom. I'm going to have you try one, but before I do that, do you have any questions about what we just did here before I have you try one? Okay, great. Here goes. You started cooking a meal at 5 p.m. and it will be done at 7:30 p.m. At 7:15 p.m., what fraction of the cooking time remains? I'll set up a poll for this and give you a chance to try it. Essentially, what we're doing here is we're creating a fraction that relates the time that remains with the total time and then reducing that fraction. So the fraction we want to create is the time that remains over the total time, and then reduce that fraction. One mistake that might be made here is making a fraction of how much time has passed already over the total time, or just sort of putting the wrong things together in your fraction, when really it's asking for what fraction of the cooking time remains. So we need to know the time that remains and put that over the total, because the total is our unit and we want to know what piece of that is left. We'll go another 30 seconds on this and then talk about it. All right, let's see where we are on this one. Okay, strong agreement, not unanimous. That's not a bad place to be. That gives us something to talk about. So let's go ahead and talk through this one. So as it turns out here, it's 7:15. What fraction of the cooking time remains? And that's 15 minutes that remains out of the, let's see, 5 to 7:30. That's 2.5 hours, which we saw a little bit ago was 150 minutes. So I have 15 minutes left out of the 150 minutes total time. And so the units cancel each other out. They're not going to be an issue for us here. So really what we're looking at is the fraction 15 over 150 that we want to reduce. You could do this a couple different ways. You might see right away, well, 15 will go into both of those. Sure, it will. So we'll divide numerator and denominator by 15. Get 1 on top, divide by 15 on the bottom, and 150 divided by 15 is 10, and 1/10 of the cooking time remains. That's the fraction that remains. I have to be honest with you, I hadn't thought about this with the length model, but when we were doing that last one, this came to me. If anybody has questions about how we got to 1/10 here, please don't hesitate to ask those, but I kind of want to go back and do a little detour just for a minute. As we look at the length model here for a question like this one. Now, I definitely want you to work with the fractions, and I want that to be fairly comfortable. That said, if we look at the length model here, and we go from 5 o'clock to 7:30, and the time that we care about is 6 o'clock here. So if we decided, well, what could I chop this up into that would fit? I could chop this up into half-hour segments. I could put one here at 5:30, and I could put one here at 6:30, and I could put one here at 7 o'clock, so that it would land here on the 7:30. That's why we chopped it into half-hour segments. And if I chop this into half-hour segments, then I can see, okay, well, what time is it now? It's 6 o'clock, which is right here. And I have 1, 2, 3 out of 1, 2, 3, 4, 5. So 3/5 of the cooking time is what remains. I have to be honest, I hadn't thought about using the length model to actually solve this. Courtney did, which is great. A lot of times, way back at the beginning of the semester, we say there's often more than one way to do something. Writing it as a fraction and reducing is kind of what we're talking about in section 2.2. But because we've already talked about the length model, it shows up as a really useful tool here. It also could be useful in this one. If we go from 5 to 7:30, and it's 7:15 now, which means I've got to cut this up into 15-minute pieces. So I've got 7 o'clock, 6:45, 6:30, 6 o'clock, 5:45, 5:30, 5:15. We cut it into 15-minute pieces because, well, that's what we had right here to work with. We had this 15-minute piece, and then I can see that there is 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9. I missed one somewhere, didn't I? 6:15. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total pieces, and 1 left over. So it's 1/10 of the remaining cooking time. So honestly, I hadn't thought about using the length model here, but it works beautifully. Also, rewriting it as a fraction and reducing works really well too. One more thing before I wrap us up for today is this. Just in your homework, you're going to see a couple of questions that are fairly abstract in nature. Numbers 48 and 50 are pretty abstract. They're about A and B and something being less and something being increased. And if you increase A and you increase B, and I think they're excellent questions that I want you to play with, but since they're abstract, they can be a little bit hard to wrap your head around. When you're given an abstract question, if it's hard to wrap your head around, put some numbers in there and try it with actual numbers. And that's a really good way to make sense of it. And that'll help you answer those questions. And that's going to be true for 48